Bismillah, Assalamualaikum warahmatullah. You're listening to microbiology lesson on microscopy. This is part 3, and in this episode we're going to cover the common types of electron microscopes. As I mentioned in the first part of this lecture, the electron microscope was invented by the Hungarians and Germans. You can still see the replica of the first electron microscope in Deutsches Museum in Munich. It's beautiful in the classical sense, with the needle meter to show the voltage instead of a digital screen, and they have a wheel controller that you have to turn by hand, because this was before the advent of the modern computer. It reminds me of the scenes in Captain America, the first Avenger. Our contemporary electron microscopes, on the other hand, share the basic shape, but as expected, they are highly connected to computers or digital equipment. I don't think I mentioned this last time, that even light microscopes nowadays are mostly digital microscopes, especially the ones that you would find in well-funded research labs. So, in some textbooks, they have a category on digital microscopes. I don't think that's necessary. Most microscopes, if not all of them, are going to be digital. That's also something that you might find interesting in terms of potential career path. If you are interested to work in microscopy, it can be worthwhile to take electives related to computer programming, because more and more microscope inventions and maintenance will need programming knowledge. It might give you that digital edge compared to other microbiology students. Okay, so light microscopes and the electron ones both illuminate the specimens to generate images that our eyes can see, but the electron microscopes use electron beam instead of light beams for the illumination. And that makes a massive difference, because electrons, when they behave as a wave, they have much shorter wavelength than the light wave. And because of this, they can separate two objects better. They can get higher resolutions. Remember, in the last episode, you learned that your compound microscope can magnify stuff 1000 times, like 1000x. So that's good already. But electron microscopes can magnify things hundreds of thousands of times, even millions of times. It's just, subhanallah, it's crazy. So, we're going to talk about 3 types of electron microscopes: the scanning tunneling microscope, the transmission electron microscope, and the scanning electron microscope. I want to go with the scanning tunneling microscope first, because it's very different than the one you learned before, and then the other 2 microscopes will be easy. So what you have for this scanning tunneling microscope is a probe. Think of a probe like a needle. This is a super sharp needle. The tip of it is the size of one atom, theoretically speaking. So this probe will travel around the surface of your specimen. In other words, it scans the surface of your specimen. While scanning, the atom of the probe will interact with the atom of your specimen. Or more specifically, if you go closer, the electron cloud of your probe interacts with the electron cloud of your specimen. And this interaction causes quantum tunneling to happen. That's why we have the word tunneling in the name of this microscope. Tunneling is, you see, electron clouds, if you remember when you learned chemistry, electron clouds are not like clouds of solid electron balls floating around. Electron clouds are more like waves of probability, wave function. So the wave of your probe and the wave of the specimen can overlap. They can be on top of each other. And when this happens, their electrons can probabilistically be found in each other's atom. So you can find the probe's electrons in the specimen, and you can find the specimen's electrons in the probe. So that's roughly what tunneling means here in our context. Now, we can set this tunneling phenomenon to have a current, and we can use that current to sense the surface shape of the specimen. So when the current is stronger, it indicates that at that position, the specimen's surface is closer to the probe, like the peaks of mountains that are closer to the sky. And when the tunneling current is weaker, it indicates that at that spot, the surface of the specimen is farther away, like valleys that are farther away from the sky. So the probe can sort of feel the shape of the whole surface of the specimen. So imagine, yeah? So if you're in front of your laptop, try this. Close your eyes. Then move one finger around the surface of your keyboard. Now your finger feels the surface of your keyboard, the shape of the surface, right? So that's kind of how the probe feels the surface of your specimen. And that data then will be amplified and processed by the computer. And then the computer will put the image together. And a variant of it, called atomic force microscope, can even construct a three-dimensional image. So you can see the surface of a cell in such details down to atomic resolution. You can even see, for example, the budding scar of one cell of Saccharomyces cerevisiae. So that's how powerful the scanning tunneling microscope is. For the transmission electron microscope, it is basically a big tube with electron beam inside. Inside the tube, at the top, there's an electron gun. I know it sounds like a futuristic weapon. I wish it is. But this electron gun simply has heated cathode filaments, which are basically thin metal threads. So this electron gun fires an electron beam downward. Under the electron gun, you have anode and gun alignment coils. So these anode and gun alignment coils, they help focusing and speeding up the electron beam. Under the alignment coils, you have a condenser aperture and a condenser lens. Remember, this condenser system is not made of glass like what you learn in light microscopes, because we are in the electronic illumination system now, not light illumination anymore. So the condenser system is made of magnetic metals instead of glass. So this condenser directs the electron beam to the sample. But before the electron beam gets to the sample though, the beam goes through an objective stigmator. So that's stigmator, stigmator. We don't have the stigmator in light microscope. We have it here for the electron microscope to prevent the electron beam from being distorted, from going to the wrong directions. And then the beam is directed towards the sample holder. The sample holder is the equivalent of the stage in light microscope that you learned before. Now, this is important. The sample has to be extremely thin, less than 100 nanometer. We want the sample to be so thin so that electrons can transmit through it. When electrons can transmit through something, that area will become brighter in the final image. The surrounding of the samples then has to be thicker. The thick area will scatter the electrons. So the scattering of electrons will make the thick area darker in the final image. After passing the diffraction lens, the electron beam will go through objective lens, diffraction lens, and objective aperture. All these components will redirect both the transmitted electron beams and the scattered electron beams that got through. Then the beam goes to a set of intermediate lens and diffraction stigmator to correct the beam direction, and then to project the lenses that you use to adjust the magnification. And finally, the beam goes to the fluorescent viewing screen for you to see. The images that you get out of these microscopes are usually black and white, but often scientists color them digitally to help with the visualization of various structures to make them distinct from one another. Right? So that's it. Oh, this whole system of electron microscopy has to occur in the vacuum. You can't have air in it because the air particles will mess up the trajectories of the electrons. Right, so that's the transmission electron microscopes. Now, this is the last one. Similar to transmission electron microscope, the scanning electron microscope also uses an electron beam, but it uses it in a different way. The transmission electron microscope detects or collects the electrons that pass through the specimen. On the other hand, the scanning electron microscope collects the electrons that bounce off of the specimen. So that's one of their key differences. In terms of structure though, a scanning electron microscope also has an electron gun at the top. It does the same thing. It heats up and fires electron beams downward. Under it, you have anode, you have condenser aperture and condenser lens. They speed up the electron beam, accelerate it, and block electrons that go to the wrong axis, that go to the wrong directions. And below these things, you have another set of spray aperture and condenser lens. What they do is they apply a magnetic field to focus the electrons to a specific spot in the objective lens. Then under the spray aperture and condenser lens, you have the objective lens, which is usually coupled with deflection coils. So this objective lens with the deflection coils, they work together to make sure that the microscope system scan the sample in a particular manner called raster scanning. So that's R-A-S-T-E-R, raster, where they scan in a rectangular pattern. And under those objective lens and deflection coils, you have the final lens aperture where the beam will be directed towards the sample. When you shoot the electron beam towards the sample will emit electron beam back in different forms. So to catch these electrons that come off of the sample, we use 3 different detectors: backscatter electron detector, X-ray detector, and secondary electron detector. The backscatter electron detector catches scattering electrons that diverge from or go off of its original trajectories. This is useful to identify different material compositions of the samples. The second one, the X-ray detector, picks up high energy electrons. So you use this to map the dispersal or the distribution of different elements in the samples. And then the third one is the secondary electron detector. It detects low energy electrons and you use them to make topographic images, how the surface of the specimen will look like. And out of those data, the computer can put together 3-dimensional images that can be rather splendid. I personally always like scanning electron micrographs. If you see a good one, it grips you and pulls you into that level of reality at that moment in time. All right, there you go. Those are examples of electron microscopes that you should know about at this level. In the next episode, I'll talk to you about some basic techniques in microscopy preparation. Until then, keep on reading, keep on learning. Barakallahu li wa lakum. Wassalamu alaikum wa rahmatullah.